All right. So let's resume from where we left off, which is quite a long time ago because we did have an exam last week. And before that, we were talking about caching, right? So let's continue and do a quick recap on caching and memory hierarchy. So when you talk about, or when you hear the word memory hierarchy, it basically means that I would like to be able to access my data, right? So basically every single CPU at some point it needs to consume the data, which means I need to bring the data over from the main memory or DRAM, right? Because that's where your variables and arrays and everything you use in the programs actually reside on, right? So that's from the core perspective, right? And actually to go there, we have this analogy, right? Where let's say I'm hungry, I want to eat something, right? One thing I can do is I would check the lab's cabinet or like the hidden stash for any snack, right? So I can satisfy my hunger. That'll be like your register, right? If you cannot find it, you go to nearby convenience store like 7-Eleven or any like nearby mart, right? That'll be your L1 cache, the level 1 cache that's close to you. Most of the time, this L1 cache is private to each of the CPU core. And that's quite nice because it allows, sometimes we call this isolation. Basically, it means that core 1 can only access the L1 cache for core 1. So it will not have random people trying to use your cache, right? L1 cache is typically really small. It is typically timed such that to get to the data, you are spending around 4 cycles. Most of the time it's 3 to 5. So actually never really, I don't think I ever seen 3 cycle. Actually, in the spec sheet from like Intel and AMD chip, most of the time I would see something along the line of 4 cycle, right? And then afterward, let's say your data is not in the L1 cache, you would then look at a much bigger, actually it is multiple times bigger than L1, the share L2 cache. And if you cannot find it, most modern processor would have the L3 cache because I don't have a lot of room to draw on the slide. Basically, once you're in the last level cache and you cannot find the data, you then go to your DRAM, right? And when you're now in DRAM, that's where your data will guarantee your data will be there unless it gets paged out, which we'll not talk about it now. All right. So that's the memory hierarchy. These allow the core to, most of the time when you access the data, you would go to the L1 and most of the time you will find your data, right? In a rare case, you have to go to L2, then you check L2. In many cases, you find your data there. If not, then you guarantee to be able to find your data in DRAM. And it's a hierarchy of this different level of caching. All right. And the the really primitive cache design, you might be asking, okay, what's in the cache, right? So it consists of two things. The first thing are the tag store, right? And the second thing I call the data store. So 2 weeks ago, I used the movie theater example, if I remember correctly, right? This time I'll use it. Well, think of it as a storage room, right? Your data is just basically in the box, right? And you want to store in the storage room. Your data stores the actual room itself. The tag store is basically your tag on the storage, on the box, saying, hey, what is inside the box, right? The tag store will store all the tag that tells who is the owner, if you will, of this particular cache block, right? And you can use the tag store to actually um, kind of embed additional information, whether the cache is valid or not, or whether the cache is dirty or not. Then you have the data store, which has most of the time limited in size. It's not as big as DRAM, but it's basically quite big. Big enough that you can hold enough data, right? And the address is used to index. Basically, whenever you see an address, right? These are used to go to the tag store in order to retrieve the data inside the data store. So again, imagine a storage room, right? You have a bunch of boxes. If you want to search for a random items in your mind, right? What would you do is you go check the tag of the boxes, then see is that the would that box have the item you intend to find or not, right? So that's why you need the tag store, and what you want to search is the address. So what's in the tag store? First of all, you would have the valid bit. Is the data valid? There's a tag bit, which tells you what address is actually the owner of this particular block, right? And the replacement policy bit, which we'll talk about this later when we talk about replacement, but these are bits we can tag in order to determine, let's say that room is full, right? Who should be kicked out, who should be evicted. And the dirty bits, which again, we'll talk about this later when we have to deal with data rights, right? When you have to update the cache, right? Because this is quite an important topic, so let me do the same lecture in Thai so that if you try to catch up, you understand what I'm trying to say here, alright? ก็คือให้คิดว่า cache เนี่ยมันเหมือนเป็นโกดังแล้วกันโกดังเก็บของนะครับแล้วในโกดังเนี่ยเราจะเก็บเป็นกล่อง data เราอยู่ในกล่องปุ๊บใช่ไหมเวลาเรา search โกดังอ่ะถ้าโกดังมันดีเนาะมันก็จะมีแบบเป็นแถวเป็น IO เข้าไปแต่ละแถวแล้วในแต่ละแถวมันก็ควรจะมี label ใช่ไหมให้คิดว่าแต่ละแถวนั้นคือ cache set ที่เราเรียนกันในสัปดาห์ที่แล้วแล้วในเซตอะสมมุติเราเดินเข้ามาเรารู้แล้วแถวนี้แน่ๆเลย data จาก address ของเราเนาะเราก็จะaddress มันจะบอกว่าต้องไปที่แถวไหนพอเดินเข้าไปปั๊บแต่ละกล่องในโกดังอะมันก็จะมีแบบต้องมี label อยู่ว่าแบบกล่องนี้มีอะไรกล่องนี้มีอะไรกล่องนี้มีอะไรใช่ไหมครับอันนั้นเนี่ยเราจะเรียกมันว่า tag แล้วเราใช้ address ที่โปรแกรมเราต้องการเข้าถึงนี่แหละแบบเวลามี pointer มันก็คือ address นะภาษา C หรือ address ของ data เราอะเราก็จะดูจาก address แล้วดูว่าเฮ้ย address อะตรงกับ address บนกล่องหรือเปล่าถ้ามันตรงกับ tag บนกล่องเนี่ยก็แปลว่าอันเนี้ยกล่องเนี้ยเป็นกล่องที่จะมี data เราอยู่ถ้ามันไม่ตรงก็แปลว่าไม่มีนะครับส่วน replacement policy bit เนี่ยก็คือมันจะเป็น bit ที่เพิ่มขึ้นมาใน tag store เพื่อที่จะแบบเอาไว้เก็บ information ว่าเวลาสมมุติถ้าโกดังเราเต็มเราต้องการถีบแบบเอากล่องบางกล่องออกไปกลับไปเก็บใน DRAM อ่ะเราจะถีบอันไหนนะครับมันก็จะมีออปชันให้เราเตะเราก็ต้องเลือกเตะว่าจะเตะอันไหนที่จะ effective ที่สุดส่วน dirty bit เนี่ยมันจะเป็นบอกว่าสมมุติเราเขียนค่าทับถ้าเราเขียนค่าใหม่ทับเข้าไปในกล่องเนี้ยเราควรจะต้องบอกให้ dirty bit อ่ะมันเปลี่ยนจาก0เป็น1ว่ากล่องเนี้ยมัน dirty แล้วนะมีคนมาแก้ใช่ไหมครับเดี๋ยวเราจะมาอธิบายว่าทำไมต้องมีนะครับ Alright, so that's why we need the tag store essentially in Thai. The organization built a cache contain multiple cache blocks. Each blocks belong to a set. The memory address basically is mapped to a certain set, as I said earlier in Thai, actually. Basically, in the cache, there'll be multiple sets. In the set, there'll be multiple cache blocks. Your data can belong to one of the set. Basically, when you see an address, it will have the way to look up, right? Basically, an address is divided to multiple bits, the tag bits, index bits. And to get the index bit, basically each address, right? Because each address point to a unique byte. So when you look at a cache block, let's say in a CPU scenario, a 64 bytes cache block, the end least significant bits are reserved for the byte you're trying to access. So that's log2 of the size of the cache block. Sometimes I call this a byte in block bits. The next m least significant bits are reserved for the index bit. These will tell you what set do you go to. So let's say your cache has 128 sets, right? Log2 of 128 is 7, so it means that the next 7 bits are for your set ID. Let's say those 7 bits is 10, you go to set number 10. The rest are the tag bits, all right? So that's how you can go and access your cache, right? And we have the concept of set associativity, which is basically, if you look at, say, the rec map cache, right, which means that each set has one block. If I have an access that always go to the same set, they will replace each other and you never have a cache miss. So, no, sorry, my bad. You will never have a cache hit, right? So what you want to do is basically to add more blocks in a set because each address go to a unique set. It means that if I go to that set, I'll see a few blocks and I'll check, is that mine? If not, I'll get my own box from DRAM, put it here, right? So set associativity, the way you implement this, I'll have the tag store that contains a set of possible data. And a cache block is one single unit. A set would contain now multiple cache blocks that are inside the same tag or data store entry. This is called a set associative cache. The downside of this is when you look up your cache, you now need to compare a bunch of tags to actually see, is that mine, is that mine, is that mine, is that mine, rather than just going one location, no, is that mine or not, right? Then now let's continue on the content of our lecture. Basically, this will be likely new from 2 weeks ago, right? How do I insert or replace things from the cache? If you have a direct map cache, which means I have one block per set, this is simple. My address point to a set, that guy gets kicked out if it's not mine. But when you have a set associative cache, right, what it means is you essentially, right, have a few blocks, right, n blocks per set. All right, so let's say this is your set. And in this case, let's say that for 4 blocks, right? You bring in a new data, a new box, right? You have a choice. Which one do you kick out? All right, so the key issue involves 3 topics: insertion, how do we put the new things in, promotion, let's say you access item in there, how do you treat them afterward, and eviction means that how do we pick what to evict from the cache. All right, so the replacement policy, let's say it's full, let's say your cache is full, you need to find which block that match, basically the block in the set that you map to, right? What block should be evicted? This is sometimes this is called the cache replacement policy, right? And this is a design choice. This is one of the possible things you can change in hardware, if you will, right? You can replace things at random. You can do first in, first out. So any guess, any takers here on what might be useful? What, let's say if I'm giving each one of you a choice, all right, everyone, except Ajahn Buck, everyone here need to tell me which policy are you gonna pick. All right, I'll give you maybe 1 minute for this. Out of this, 1, 2, 3, 4, 5, 6, 7, 7 policies, which one might be a possible policy you would use for your cache? Any taker? Come on, I'll wait until everyone here type in something. All right. So if you rewatch this video, it's gonna be a super awkward pause here. I'm waiting for the answer from you guys. เอาละทุกคน ถ้าต้องเลือก1 policy มาจะใช้อะไรดีแคชผมเต็มผมจะเตะด้วยเตะของเก่าออกด้วย policy ไหนดี ขอบคุณมากครับเบสมีการพิมพ์เป็นคนแรก least frequently used โอเคมีใครจะleast frequently used โอเคมีใครมีไอเดียอะไรอีก How are you? Okay, perfect. All right. So we have 2 options here. Either the frequency based, right, or recency based. So right now the answer from the chat. Okay, I think it's a new person joining. Oh no. So from the chat, there are two strategy. Basically, it's frequency based. Oh. Frequency based, right? And recency based. So in most cases, you want to be honest, like let me be super honest here. You want both of them. You want to kind of capture, do I access this data frequently or not, right? Somehow we call this hot data. Hot data means it's the data I access frequently. Or I might want to keep recent data because there's a trend. right? That is likely to be used again. One of the primary issue with the frequency-based scheme is, let's say I see this block for the first time, the frequency of access of that guy would be 1. And if the block get old enough, it stay in the cache, it get reaccessed, right? The frequency would go up. But then the newly, let's say I need to get in another block, right? That are new. They would have the frequency of 1, but then you don't have the history of that guy. So the problem is the older blocks might be prioritized by accident because they stayed there for a long time and have a high frequency, right? So a frequency-based scheme, you may have to tie into the information about like how old has the block been and what's the frequency of access. Recency-based, you would then basically try to evict the sometimes called LIU, which is least recently. Least recently used, right? So this is basically would kick the guy that you haven't used for the longest time in the set. And this is basically kind of like a default policy for your hardware cache, right? I mean, in software cache, it's a totally different story, all right? In hardware cache, recently used makes sense because it's based on temporal and spatial locality, right? Basically, if I haven't used the cache for a while, I will likely not to be used it again, right? The benefit is this is likely to be effective. Here's the downside. First of all, it can be costly to implement. The reason why I said this can be costly is there are ways to kind of change the hardware implementation to make it not too costly. Also, you will have to do a lot of comparison to get the least recently used one, right? So again, the benefit is performance. Downside is hardware complexity that you have to be careful on how you implement this. All right. There also the approximation of the LIU policy, which is as long as I don't pick the latest guy, I'm okay, right? So that's called not most frequently used. Or I can do a hierarchical design of that. So let's say I have 16 way, right? So there's 16 box here that you can pick, right? You would then subdivide this into a group of 4. And you pick the not most recently used, basically not the latest guy from each of this group. Then out of this, you can again pick the only one that are not most recently used, right? So these are hierarchical design that try to approximate our EU policy that are really simple because now you just need to basically maintain 1 bit, right? For each of this group, 1 bit, say, is that the most recently used? Because if that bit is not 1, then I can kick. I can randomly pick who to kick, all right? Again, one more downside of LIU policy is called set thrashing. Set thrashing means that, let's say I have a lot of data being mapped to the same set, right? One example is, let's say I have a 4-way cache. I can maintain 4 blocks in a set, but my code goes through the pattern of access block A, B, C, D, and E that all map to the same set. Now, again, my cache, the set can contain 4 blocks. My program tries to access 5 things in the loop, A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. When you access E for the first time, right? LIU policy would kick out A because that's the least recently used block. It will replace this with E. Then the next access is going to be A, which you just kick, right? So it's going to be a cache miss. You brought A from DRAM, then try to identify who is the LIU block here. Again, now B is the LIU block. Get replaced by A. The next access is B. B comes in, it's a miss, all right? And check LIU. LIU is definitely this block, so it's get replaced by B. The next access is C. C is also a cache miss coming in, replace D, right? And you have this loop of unending cache misses, essentially. In this case, even a random policy might be more effective, right? So there are, for example, like a hybrid policy design proposed in ISCA 2006 from Win Qureshi that takes a look into, hey, can we do set sampling and pick the better policy, or whether it's the LRU or random policy, right? So that may be an even better policy for here because it tries to detect set thrashing and it tries to pick a better policy if the worst case happens, right? One more thing that we have to talk about is called ability optimal. Ability optimal is basically means that we want to be evict the block that's going to be referenced furthest by the program, furthest away. This is one of the important theory in caching, in a sense that this is impossible to implement because we cannot predict the future, right? If we do, go by lottery. Not even I'm joking, but like this is impossible to do because you need the prediction of the history, right? But this is high impact because even though we cannot implement this, we can simulate them and see how close we are to Belady's optimal for many workloads that we try, right? So when you try to let's say design a cache policy, you might be using multiple baseline, right? This is a potentially one really solid baseline to compare to. This like an ideal baseline, right? The one more message is let's say you get a lot of cache hits, right? Does this minimize execution time? No, because there are multiple things that can affect the overall performance of your program, right? Aside from eviction policy, the next thing is the insertion policy. So when you insert a new cache block, right, you can also insert at the different position if you will, right? For the most cases, the new block might be treated as the most recently used because you just literally use that block, right? When you put the block in the MIU position, basically tag this as the most recently used, it would prevent the block from being kicked out soon. But sometimes you might have a program that looks like this, right? I have an array. And you basically read through an array from index 0 to index, say, 100,000, right? How many of you write a program that has the array access like this? I go through my really big array. I mean, it's a pretty common program pattern, right? So this particular program has no reuse. If you think about it, because I never reuse my data, right? So in this case, putting the block in the LRU position might make more sense because I would then evict the block right away because I know I have no reuse, right? So the work that goes into the insertion policy, sometimes we try to detect reuse for the block, right? So basically, you try to first detect things like reuse. If there's no reuse, or this is like the last time of reference, sometimes we call this re-reference, right? Then there's no point putting them in the cache even. You can also choose not to insert to the cache or bypass completely as well, right? Then you also have the promotion policy, which means that let's say you access a block that's already in the cache, right? They are likely to be accessed again, so maybe you want to promote them to the MIU position, right? This can be done by updating the bits that are relevant for the replacement policy, depending on how you design your cache. Then the last thing is about the dirty bits, handing rights or dirty bits. Okay, so when I write to a cache block, right, the data change. What it means is remember the memory hierarchy. All right. So as I said, here's my DRAM. This is the L2. This is my L1. All right. So let's say I bring in an address, and originally this number is 5, right? So everything here is 5 and 5. What happened if my program write to this address? So let's say I change from 5 to 10. Is it hitting an L1? Is my access hitting in L1? Yes, right? It's going through L1, check the cache. Oh, it's okay, it's here. I write this, change it to 10. Okay. My question to all you here, and please answer, is in the future, if I access the same address again, do I correctly see the number 10? Is there any problem here? If I were to access the same address and read, oh, okay, it should be 10, right? Because it's to the same address and it will hit in L1. The L1 already have the updated data. But here's the issue. Let's say someone else kick the block out, right? Someone else kick the block out. It's not in L1 anymore. It's not in L1 anymore. You need to make sure this data is written back and changed to 10. Unless there's someone kick this from the L2, it's not here anymore. You need to make sure this is updated to 10 eventually. We call this process write back, right? And there are two things you can do with write backs. The first process is write through. Every time I update the data, I update everything in my hierarchy. I propagate the right data right away. This is bandwidth intensive, but it's simple. We also can have a write back policy, means that I can write to the data just in the cache block and I delay the update by flipping the dirty bit. If the block is replaced and if the block has a dirty bit of 1, it means that, okay, now I know that I have to write the L2 and update the data to say 10 in the example, right? Because this is quite an important topic. Again, let me do this in Thai. All right. ก็คือเวลาเราอัปเดตข้อมูลใช่ไหมสมมุติเรามีโปรแกรมเขียนแล้วค่าเนี่ยสมมุติเราจะต้องการอัปเดตตัวแปรจากค่าที่มันเป็นค่า5เป็น10จาก5เป็น10เนาะสิ่งที่เกิดขึ้นก็คือไอการอัปเดตค่าเนี่ยมันจะไปฮิตใน L1 เพราะเราใช้ค่านั้นใช่ไหมใน L1 น่ะค่ามันจะเปลี่ยนจาก5เป็น10แต่ว่าไอ address ตัวเดิมอ่ะมันจะมีอยู่ทั้ง L2 แล้วก็ DRAM ใน L2 กับ DRAM มันจะไม่มีใครไปอัปเดตมัน เพราะว่าไม่รู้โอเคยังเก็บค่า5อยู่ใช่ไหมก็อย่างที่ผมเอาให้ดูในที่วาดเมื่อกี้เนี่ยตอนแรกค่ามันเปลี่ยนจาก5เป็น10 L1 รู้อยู่คนเดียวแล้วมันก็ยังโอเคผมก็รัน CPU ผมรันได้ เพราะว่าถ้าผมต้องการใช้ค่าเนี้ยมันก็จะเป็นแคชฮิตอยู่ใน L1 ก็โอเคค่า10ใช้ต่อกรณีที่มันจะใช้ไม่ได้กรณีเดียวก็คือว่าตอนที่มันสมมุติบล็อกเนี่ยมันถูกแตะไอ้ค่าที่มันเก็บค่า10เนี่ยมันถูกแตะไปจาก L1 แล้วอ่ะโดยคนอื่นหรือโดยพาร์ทอื่นของโปรแกรมใช่ไหม L2 มันยังเป็นค่า5อยู่เพราะฉะนั้นถ้าเรามี dirty bit ก็คือสมมุติเราเขียนค่าอะไรสักอย่างอยู่ใน L1 ปั๊บเราจะเซต dirty bit จาก0เป็น1ตอนที่บล็อกนี้ถูกแตะมันก็จะไปเช็คแค่ว่าเฮ้ย dirty bit เป็น0หรือ1วะถ้าเป็น0แปลว่าไม่มีใครมาเขียนค่าเซฟไม่ต้องทำอะไรถ้า dirty bit เป็น1แปลว่าเฮ้ย L2 ต้องเอาค่านี้ไปอัปเดตด้วยนะเพราะว่าถ้าไม่อัปเดตพี่จะเป็นค่าเก่าอยู่เพราะฉะนั้นถ้า dirty bit เป็น1ปั๊บมันก็จะไปอัปเดตค่าใน L2 ให้มันเป็น10แล้วถ้าใครเตะบล็อกนี้ออกไปจาก L2 มันก็จะไปดูเช็ค dirty bit เหมือนกันมันก็จะไปเช็คdirty bit เป็น1นี่หว่าก็เก็บไปวิ่งไปที่ DRAM แล้วก็บอกว่าอัปเดตค่า address นี้ให้กลายเป็น10ด้วยนะครับมีคำถามไหมครับมีคำถามไหมมีคำถามไหม
ช่วยอธิบายอีกรอบหนึ่งจะได้ไหมครับ
ได้
ครับ
สมมุติผมมี CPU อยู่ตรงนี้อันนี้เป็น L1 ใช่ไหมครับ L2 แล้วก็ DRAM แล้วก็สมมุติ CPU อ่านค่า address I address A เนาะคือ address A แล้วค่าตรงเนี้ยมันเป็น10อยู่10ก็ได้เราอ่านค่าได้10ค่าของ A เป็น10แต่แล้วเราก็รันโปรแกรมแล้วเราต้องการเปลี่ยนค่าจาก A จาก10เป็น20แล้วกันจะเกิดอะไรขึ้นอันนี้ไอ address A ทั้งหมดตรงเนี้ยมันก็จะแบบเฮ้ย hash L1 มี address A เปล่ามีเจอก็ cache hit ใช่ไหม cache hit ต้องการเขียนค่าเป็น10เดิมค่าเดิมมันเป็น10ต้องการเขียนค่า20ทับเข้าไปก็ตุ้ม อันนี้ยังเข้าใจกันอยู่ใช่ไหมฮะก็คือผมก็แค่เช็คเฉยๆเปลี่ยนค่าเป็น20ปัญหาที่อยู่บนสกรีนบนจอตอนนี้คืออะไรเอ่ย
เลเยอร์อื่นไม่อัปเดตแล้วครับ
ใช่แล้วเลเยอร์อื่นไม่ได้อัปเดตผมแก้ได้2 วิธีวิธีแรกก็คือผมใช้ write through ถ้าผม write to ปั๊บก็คือทุกครั้งที่ผมเขียนอะเลเยอร์ทั้งหมดเป็น20หมดเลยคือผมก็ต้องส่งแพ็กเกจไปที่ L1 บอกให้อัปเดตเป็น20ด้วยส่งไปที่ L2 อัปเดตเป็น20ด้วยอัปเดตไปที่ DRAM เป็น20ด้วยโอเคอันนี้เป็น write to policy โอเคอันนั้นเคลียร์ไหมฮะ write through ทำงานยังไงเคลียร์เนาะ
โอเคครับ
แต่ write through เนี่ยข้อเสียของมันก็คือมัน bandwidth intensive เพราะว่าทุกครั้งที่ผมเขียนอะผมต้องเขียนทุกที่เลยมันเสียเวลาคือไม่มีแบบไม่มันก็ make sense ที่จะทำแต่ว่ามันจำเป็นไหมเพราะว่าผมจะถามคำถามต่อไปถ้าผมต้องการ access address นี้อะมันจะไปฮิตอยู่ใน L1 แบบมันจะมีโอกาสอะไรไหมที่แบบอยู่ดีมันต้องแบบวิ่งไปที่ L2 ทั้งที่ L1 มันมี data นี้อยู่ มันเป็นแคชฮิตอะใน L1 มันก็จะบอกโอเค L1 แคชฮิตนะวิ่งมาละถูกละ20ก็ได้ค่าที่ถูกต้องใช่ไหมครับคือผมสามารถดีเลย์การอัปเดตได้เพราะว่าผมใช้ address เปิดไว้ใน L1 ผมก็เจออะมันอยู่ตรงนั้นอะนี่ใช่ไหมครับกรณีเดียวที่ผมต้องอัปเดตคืออะไรเอ่ยเอากรณีเดียวที่จะต้องอัปเดตคืออะไรครับ
ต้อง access จากเลเยอร์อื่นด้วยนะครับ
ก็คือกรณีที่ต้องอัปเดตก็คือ L1 ไม่ได้เก็บบล็อกนั้นแล้วอ่ะคือใครก็ไม่รู้เผลอทีบบล็อกนั้นออกไปมันจะเป็นมิสใช่ไหมฮะมันก็จะกลายเป็นแคชมิสแล้วก็จะวิ่งที่ L2 แต่ L2 อ่ะมันจะเป็นค่าเก่าอยู่เพราะฉะนั้นตอนที่มีใครมาเตะบล็อกนี้ออกไปอย่างเงี้ยนะก็คือเราจะรู้กรณีที่ต้องอัปเดต L2 อ่ะก็เพราะว่าถ้าใครมาเตะบล็อกเนี้ยออกไปจาก L1 อ่ะเรารู้ว่า L1 เป็นคนเดียวที่มีค่าอัปเดตไปอัปเดต L2 ด้วยเพราะมันจะไม่อยู่ใน L1 แล้วอ่ะเห็นภาพไหมครับอันเนี้ยเขาเรียกว่า write back ถ้า write back ก็คือสมมุติผมโดนเตะตุ้มออกไปจาก L1 คือไม่มีบล็อกนี้แล้วนะ L1 ผมก็จะบอกว่าเฮ้ยเราจะไปเช็ค dirty bit ถ้า dirty bit เป็น1แปลว่ามีใครมาเขียนแอบเขียนแล้วก็ไปแก้ L2 ให้ด้วยเข้าใจไหมครับหรือว่ายังงงอยู่
โอเคครับอาจารย์
โอเค alright so that's how you can handle writes okay on the right miss you also have a choice to just skip basically sometimes you actually like you don't have to allocate the cache block, right? So you can allocate on a write miss is simpler, right? Treat it the same as read. You can also not not use the cache. Basically, let's say you know that the block are not going to be reused, right? You can choose to doesn't write the block to the cache. Okay. Now, in terms of the cache miss, there are 3 types. There's compulsory miss. This is basically the data seen for the first time. There's nothing you can do. It's going to be a miss, except when you do prefetching. Prefetching are special instruction that you can issue and say, I know I will need this address. Get me this address beforehand. The CPU will then try to get the data into your cache beforehand. Conflict miss means that the data map to the same set and it conflict because the set is full. Capacitive miss means that the cache is just full, the whole thing is full, right? So both conflict and capacity myths can be solved or addressed through better management of the data in the cache. Basically, try to figure out who should be in the cache and who should not be in the cache. All right. To measure performance, you generally will look at things like cache miss or hit rate. The cost of each of the hits and miss, right? Basically, if I hit, how long does it take to access my data? What's the time does it take if I have a cache miss? And also the total cost of the data load. Basically, what's the average latency given the L1, L2, L3, or level 4 or DRAM, and with the hit rate and with the access latency. All right. So let's say you write a program, you want to improve your program performance, you can definitely try to refactor your program in a way to reduce miss rate. You can change the hardware and add more associativity to the cache or add more cache, essentially. You can also even do things like prefetching. You can also try to reduce the miss latency by adding more cache level or do prioritization or do sub-blocking. These are basically some of the ideas are listed on our reading list for the class. So if you're curious, feel free to check them out. You can modify the replacement or insertion policies, or even things like allow multiple cache misses in parallel, or having multiple cache accesses per cycle. All right. You can also try to rewrite your program to improve performance by doing things like even like loop unrolling or subdivide the loop using divide and conquer so that they touch a few more addresses so that the whole thing fit in the cache. You can also try to reduce the number of memory access because memory access typically takes a long time to finish. Okay. I know this is like a refresher for many of you. So in the next, basically after we talk about DRAM, we'll start to dive deeper into research. So I'll bring up a mix of multiple works that look into the entire hierarchy from cache to the memory to DRAM to virtual memory on how they would address this problem in a research level. That's kind of like the wrap for the background, basically background for the caching. I'll then transition into the background about virtual memory, which also has a lot of research right now, including many of my research as well. Most of my work are more on the accelerator and GPU VM, but still, nonetheless, they're really relevant in modern day computing. So before we transition there, let's take a quick break. Let's say we resume at 10 o'clock. All right. Okay, so I'll stop the recording. So we have multiple sessions for the recordings. I'll post this on YouTube like usual. All right, guys.